All right, well, it's my pleasure to introduce our next speaker, Cynthia Rudin. Cynthia Rudin is a professor of computer science, electrical engineering, and computer engineering, statistical science, and biostatistics and bioinformatics at Duke University. She is the director of the Interpretable Machine Learning Lab. So Jorn's comments about black boxes and interpretability are a nice segue into this topic as well. She's done a lot of work in building machine learning models that are powerful in terms of accuracy and prediction, but also interpretable so that humans can understand them. She is the recipient this year of the Squirrel AI Award for Artificial Intelligence for the Benefit of Humanity, which is given by the Association for the Advancement of AI. And this prize is called the Nobel Prize of AI. This is only the second time it was given. And she's a fellow of the American Statistical Association and a fellow of the Institute of Mathematical Statistics. Her work has also been featured in a lot of news outlets, including the Washington Post and the New York Times, as well as books. In fact, I'm reading a book right now called The Alignment Problem, and I happened to be reading it a couple nights ago and stumbled onto a section about Professor Rudin's work. And it was a very nice serendipity and made me look forward even more to her talk, which I was already very much looking forward to. So thank you, Cynthia.
My pleasure. Okay, let me share my screen here. Hopefully you guys can hear me and see me okay?
Yes.
Great. Okay, so I'm going to discuss work in the Almost Matching Exactly lab at Duke, which is run by 3 professors. It's me, who works in machine learning, Alex Wolfowski, who's an expert in causal inference, and then Sudeep Roy, who does databases combined with causal inference. All right, so I want to start with some examples of observational causal inference problems that could occur in supply chain management. All right, so let's say we wanted to answer a question like, how much would a supply chain disruption impact panic orders and excess inventory? Or, and this is a causal question because it's like A implies B, but it's not really a question where you could do an experiment because you don't want to disrupt the supply chain to get the answer to the question. So here's another question. Does excess inventory lead to cause abnormal stock returns? Okay, and there are a lot of questions like this where it's a question of what causes what and not just can we predict something. But answering these questions can be really complicated because of the presence of other variables. So for instance, well, you could say disruptions often occur when there's political instability. Was political instability the cause of the panic orders? Could that have led to the stock returns? You know, how do you examine this when you have all these variables that are sort of interacting with each other and you want to know whether A causes B? And so, yeah, these are questions that are correlation. They're not correlation questions; they're causal questions. And so the idea is that the supply chain is complex. You don't necessarily even want to create a mathematical model for it. You want to use your data. You can't do an experiment because you can't change something. You can't disrupt the supply chain, and you have to work only with observational data. Okay, that's the setting that I'm in today. Okay, so just some notation here. I'm in situation X. I changed policy T. How would it affect outcome Y? All right, so X, T, Y. Those are my variables that I care about here. All right, so what if for each supply chain disruption, we found an almost identical set of conditions for which there was no disruption? So we found essentially identical twins, and we can sort of simulate what would have happened if we'd done a randomized control trial. So these situations have same time of year, same political situation, same demand. So we control for everything else. And then we can take those matched groups and compare their outcomes and estimate causal effects from that. And this is matching. And it is an extremely powerful type of technique for observational causal inference. It mimics a controlled experiment because you're controlling for everything else. And the goal is just to use these matched groups so that you can figure out whether A causes B. All right, so I'm gonna, oh, by the way, I should tell you, matching, it's really one of the most fundamental techniques in estimating cause and effect of treatments. It's used widely across the social sciences. It's used in medicine, and it can allow us to examine causal impacts in a way that affects demand, productivity, supply, lots of different aspects of supply chains. But in this talk, I'm going to use a healthcare example, which is kind of a quintessential example, which is how will this drug affect this patient? That's just the easiest way to sort of explain this. And the patient comes in, okay, we have our patient, and we find a match group of patients kind of like that patient, some of whom got the drug and some of whom didn't. And from there, we look at the outcomes of those patients, and we compare the ones that got the treatment to the ones that didn't get the treatment. And then we estimate the treatment effect by averaging the outcomes for the control units and averaging the outcomes for the treatment units and comparing them. And so from there, we get an estimated treatment effect. So here it's like 1.83 units, and whatever units the outcome is, like what blood concentration units or whatever it is. And like I said, matching, it dates back to the beginning of causal inference. It's a well-known way of handling problems like this. And it's great because it's non-parametric, which means it's powerful, it can fit data really well, and it's interpretable because doctors can look at the data and they can look at the match group and do a chart review. To be honest, I can't even think of a better type of technique for interpretable causal inference. It's like an all-purpose, powerful, general type of technique. Now, ideally, you'd get a great match group for every single unit in the data set, but in reality, you can't, because if you have high-dimensional data, you run into this problem that you can't find identical matches because there's no identical twins. So most of the time, people are not exactly the same. They differ on some dimension. So, since you can't match people on all the covariates, you have to pick which covariates to match people on. And as long as the things they differ on are not important, then it's okay. So here they're all wearing different things than their partner, which doesn't affect health outcomes or anything. So that's still okay. Still fine to match them. So in general, you want to match on as many good covariates as you can, but picking which variables to match on is tricky. It's actually really tricky, and that's why I co-founded the Almost Matching Exactly Lab. And so yeah, why did we start this lab? And we started it 5 years ago because the techniques out there were not good. So let's think about some of the historical techniques, the most popular ones: propensity score matching, prognostic score matching. And so here, what these techniques do is they take the data and they project it all down to one dimension. And for propensity scores, it's the probability of being treated. And for prognostic scores, it's the estimated outcome given that you're in the control group. And so you just give everybody a number, and then you match people based on how similar they are on this one axis that you've projected to. But the problem with this is that it's not interpretable. Like, you're matching people who have covariates that are totally different from each other because they have the same probability of being treated. And so you can't really do chart review. You can't troubleshoot this. It doesn't really work. So fine, let's talk about other techniques. So there are these other techniques that are called things like optimal matching, linear balance constraint matching, genetic matching. And these methods constrain on covariate balance, but the match groups are still not interpretable. They make sure that you have an equal number of women and men in each group and whatever. But the problem again is that you're matching people together that, yeah, they obey the balance constraints, but the match groups are just not interpretable. And so again, you can't do chart review or whatever it is, and do all kinds of troubleshooting that you might want to do. And these methods are pretty flexible. Like, you can make them do other things, but then you'll run into the problem that I'm going to talk about on the next slide, which is that if you think about a method like coarse-end exact matching, that's where a human puts a whole bunch of bins in this high dimensional space and just plops the people into the bins. And then you match people if they're in the same bin. Of course, the problem with this is that sometimes you have people that are almost identical in different bins. And sometimes you haven't made the bins fine enough in places where things change rapidly. So you're basically forcing the human to essentially decide on high dimensional functions in their heads, but no human can realistically do this. So yeah, and that's because the distances between units are not learned. They're chosen by a human manually. The human has to manually choose some high dimensional distance, right? Some binning in their head. So You also could do black box machine learning, which does learn the distances between units, but that is totally uninterpretable, right? You just get that the estimated treatment effect for each unit is some complicated formula for lots of variables. And so you really just can't troubleshoot it. You can't do chart review. It's really hard to think about trusting such models. And we've also found cases where you run a black box machine learning method and the result was garbage and you don't know why and you can't troubleshoot it. So our lab, what it tries to do is to match units almost exactly on the covariates themselves. And the matches are interpretable, which allows the user to troubleshoot them much more easily. We also had some extra things we wanted about our matching methods. We wanted them to run fast because we wanted to run them on big data sets. We wanted everything to run really quickly. We wanted the algorithms to be able to be used on data sets that were so big that they didn't even fit into main memory. And we also wanted to learn the distance metric using machine learning on a separate training set. So we would take part of the training set out, learn the distance metric on the training set, and then take that distance metric and then use that to figure out how to do matching. And so that's what our methods do. So we've designed so far 4 software packages, and I'm going to show you how a couple of them work. And I'm going to start with Malts. I'm just going to show you by example, because I think that's the easiest way to understand what Malts actually does. So Malts is it's matching after learning to stretch. So the distance metric is going to be a stretched Euclidean distance metric. All right, so this method creates an interpretable stretched distance metric that stretches the covariates according to how important they are. So for instance, if age is very important, it'll stretch age out a whole lot so that in order to match on age, the units have to be very close in age. And if a variable is not important, then it will just collapse the variable. Like it'll stretch it, instead of stretching it out, it'll just collapse it. So for instance, if race is not important, it'll just collapse the races all together so that even if units have very different races, then it doesn't matter. Their distance will still be 0 because that covariate has been collapsed. Okay, and the stretch of each covariate is determined from machine learning on a training set. Okay, so here we're in the most basic setting of the potential outcomes framework. X is patient covariates, Y is outcomes, T is a drug in this case, and then we're going to use the Y's to estimate what would happen if the patient is treated versus if they weren't. And another example is what we're going to see in the Lalonde dataset that I'm going to show you results from on the next slide. But here you have a person, and then the outcome is their salary. The treatment is whether they've had a job training program. And we want to figure out whether the job training program impacted the person's salary after they took the program. Okay, so let me show you how Malts works by showing you this example. I'm going to show you results actually from a couple of different methods. I'll show you a match group from prognostic score matching, and then I'm going to show you a match group from Malts. So this is a unit here. This is a person who had the job training program. They're 22 years old. They had a 9th grade education. They're not Black. They are Hispanic. They are not married. They indeed have no degree because they've only had a 9th grade education. And they had no income in 1975. So this is our query unit, and we're trying to find a match group for this query unit. And then here's going to be the treatment. This is all X, and then this is Y. And then this is the match group that prognostic score matching gives you, okay? So here, so great, we have a variety of treated and control units, great. But the problem is that we're matching people who look totally different from our query unit. Like this person's 22, why are we matching them with like 44-year-olds? This person had a 9th grade education, why are we matching them from people who graduated from high school? This person is not married, why are we matching them with married people? And then this person doesn't have a degree. We're matching them with people who had a high school diploma. And then this person had no income in 1975. Why are we matching them with people who made $37,000 that year? Okay. So it's a little funky to think about this match group. That's not something that's easy to sort of rationalize or troubleshoot. So if, on the other hand, if we look at the match group from Malts, it's just much more cohesive. Like here, we have the other people in the match group are all between 21 and 24 years, or 20 and 24 years old. All of them have had either 8th, 9th, or 10th grade education. Our method figured out that race was not important to this question, and so it just didn't care what race the people had. And then nobody was married, nobody had a degree, and nobody had any income in 1975. And so from here, we can divide the people into treatment and control, and then look at their outcomes and figure out what the effect of the treatment was on this. We can estimate what the effect of the treatment was on this unit. And so what I want you to take away from this is that given the same query, we get completely different match groups depending on the method we use. So to use Malts, what we do is we divide the data into a training set and a matching set. We use the training set to determine how to stretch each covariate. And then we use that stretch matrix as our distance matrix on the matching set to find the nearest neighbors in the matching set. And then we use the neighbors as the match group and then estimate treatment effects from the match group. So that's how the whole process works. That's how we leverage our training set to learn the distance metric. And then we take that learned distance metric, bring it back to the matching set, find our neighbors, and that's our match group. Now, in our experiments, Malts was as accurate as in estimating treatment effects as the black box machine learning techniques like causal random forests and causal BART, but it had the advantage of being interpretable. So let me switch over to talking about a different one of our software packages. And in particular, I'll talk about the Dame-Flame package. So Dame and Flame are sister algorithms. Flame works on very, very large categorical data sets, and Dame works on smaller categorical data sets, but produces higher quality match groups than Flame. And so what we typically do is we run Flame for a while and reduce the size of the data set until we can get to a data set that's small enough to run Dame. Okay, so whereas Malts was suitable for both continuous and categorical data, this particular package is only for categorical data, but it works for, like I said, huge data sets that are so big that they don't fit in memory. And the idea of them is that they match exactly on as many useful covariates as possible, and they scale these huge data sets. And so where Malts used a stretched Euclidean distance, FlameDame uses an adaptive weighted Hamming distance between units. Okay, so the goal again is to match treatment and control units almost exactly, and to match exactly on the largest set of good covariates that together can predict the outcome well. Okay, so here, for example, these are our two units. We'll look at what they match on exactly, and then we'll forget about the stuff that isn't important because we figured out from our training set that it wasn't important. Now, the prediction quality of a set of covariates, again, is determined from machine learning on a separate training set. It handles very large data sets, and it works fast due to a combination of bit vectors and database queries. Okay, so the idea is that the unit shows up, and we say we want to estimate the treatment effect for that patient. So which units do we match that patient to? And then the training set shows up and says, well, I think we should match her on covariates 9, 2, 3, 14, and 6. It's like, well, how did you know that? Where did you come up with that? And the computer says, well, there is a machine learning model that uses those same covariates that predicts the outcome well on the training set. And there's also a control unit in her match group, so it's actually a valid match group. Because it's not a valid match group if it only has treatment units or if it only has control units. So it picks the largest number of covariates, good covariates it can match on, such that there's both a treatment unit and a control unit in the match group. All right, so to just show you some notation here, there are these two groups, as I mentioned, the training set and the matching set. And then the output, of course, is for each unit, you want to provide the match group. and that match group is constructed on the matching set. So it's all units I prime in the matching set such that I prime is matched with unit I. And I haven't told you what this theta is yet. It's like a mystery theta that showed up here, but I'll tell you what it is. It's an indicator for which variables to match unit I on. Okay, so as I mentioned, theta is a variable selection indicator. Just tells you which covariates to match on. And this is, again, the equation for the match group. And I just want to show you kind of what this means here. So this is, I is in the matching set such that, I prime is in the matching set such that it agrees with I on all the covariates defined by theta. So let me just write this notation out, because it's a little bit confusing. So let's say that theta has pinpointed variables 1, 2, and 5 to match on. So then if unit I looks like this, that's the covariates, then theta says, well, I only care about matching on 1, 2, and 5. So we don't actually care what the other variables are. And I'm going to match anything to everything in the database can be matched to unit I that agrees with it on these 3 covariates. So everybody who has blue for the first covariate, everybody who has yellow, and then female, those all get matched together in a big match group. Okay, so what that means, what this notation means, is that as long as you know theta, that is sufficient to define the match group for I. So for each I, if you have theta, you know what the match group is. So we have to figure out what theta is. And we get theta from, again, the training set. So we run least squares on the training set. So this is the minimum of squared error. So that's just running least squares on the training set. And that determines the quality of a set of variables theta. Because if you take a subset of variables and you run least squares, then you know how useful that subset of variables is. And so that determines the match quality. That determines the quality of a match group. So as long as theta has a low prediction error, we say it's okay to use for matching. In particular, we say, like, as long as you're within 5% of the minimum, as long as you're within 5% of using all covariates, then we're allowed to use it for matching. So in other words, theta contains enough variables to predict the outcome well, as long as it has low prediction error. Okay, so this whole thing is kind of a balance between how many variables you can squeeze into theta, but then if you choose too many, you can't find a control unit in the match group. So your job is to stick as many variables as possible, because that'll help minimize the squared error. But you can't match unless you have both the treatment and control unit. So you can't include too many variables. And that balance is what this whole thing, what this whole thing deals with. And as I mentioned, we follow this 5% rule of thumb, where as long as we stay within 5% of the error rate from all covariates, then we say it's okay to use for matching. And there are going to be some units that can't be matched, but that's okay, because then those units are actually outliers. They're actually too far out to match. Okay, so this is the equation that our algorithms try to solve. They try to find the theta star for each I in the matching set, which again minimizes the predictive error on the training set, subject to a valid match being in existence. Okay, so let me go through this more slowly. For treatment point I want to find the set of covariates, covariates theta, that together can be used to minimize error on the training set. So they have a low predictive error on the training set, such that there's a control point in the matching set that matches I on those covariates. Okay, so you try to have the most covariates as you can, keep the predictive error low, but you still want to maintain that there's a valid match group. Okay, and like I said, there are going to be points that you can't match, and that's okay, because those are outliers. There's no set of covariates that you can match those guys with that together can predict the outcome well, and so you just give up on those points, because there's no way to estimate treatment effects. They're outliers. Okay, so we did so let's say that we do, let's say that we would do an experiment where the first 10 out of 40 covariates are relevant. Okay, let's just say that we're doing this experiment. I'm just telling you, I'm just happening to tell you that you have 40 covariates. They are less important as you go down, and then the top 10 are important, but the rest are not important. Okay. So the flame-DAME algorithm, starting with flame, will match covariate subsets in this order. So first it'll match on all the covariates and get all the exact matches. So these are units that are the same on all 40 covariates. Then those are done. Then you go to the training set and you say, okay, which covariate can I eliminate and not cause any harm? And it'll say, well, I think 40, you can eliminate covariate 40 and not do too much harm to the predictive error on the training set. So we say, fine, we'll find all units that match exactly on covariates 1 through 39. So great. So from there, I need to eliminate something again because I can't find any more exact matches on covariates 1 through 39. So I go back to the training set and I say, what can I eliminate without causing too much harm to the predictive error? And it says, you should eliminate covariate 39. So you do that and you keep doing this, going back and forth to the training set to figure out which variable to eliminate. And you just do this over and over again. And those are flame iterations. So these are backward elimination. This is like a backward elimination procedure where you iteratively create matches and eliminate variables that are not as useful. And then when you have a small enough number of variables, you can start using DAME. And I said DAME is more expensive, but it gives you higher quality solutions because DAME puts variables back in between when it eliminates them. So DAME, at this point, you have only variables 1 through 10 left. DAME would say, okay, you should eliminate variable 10. I'm going to do exact matches on variables 1 through 9. Then it would put 10 back and eliminate 9 instead. And then could eliminate 9 and 10 together, or it could eliminate variable 8, whatever it wants to do, depending on what the training set says. But it would never eliminate both 9 and 10 together until it had eliminated 9 and 10 separately. And so this kind of resembles the downward closure property of algorithms and data mining. All right, it's kind of similar to like the a priori algorithm. Okay, and then at some point you will have to stop eliminating variables because if you eliminate anything else, you won't be able to predict the outcome and then you'll be done. So I want to show you a result, just a kind of example of the result that it produces. This is on the natality data set. This is a big data set, 2.1 million pregnant mothers, 75,000 of them smoke, okay? So in fact, they smoke more than 10 cigarettes a day. And what we're trying to do is figure out the effect of smoking on the risk of abnormal child health outcomes, and in particular, birth weight. The treatment is that the mother has to smoke at least 10 cigarettes a day for the duration of the pregnancy. The control group smokes no cigarettes. And we just want to know, does this smoking affect the child's birth weight? Okay, so it's, like I said, a big data set. Here are the covariates right here. And I want to show you the results. Okay, so what I'm plotting is the number of treatment units in each group. And this is the estimated treatment effect. And what you can see here is that by and large, the treatment effect is mostly negative, which indicates that babies who are born to mothers who smoke tend to be lower weight because of that smoking. And we've controlled, like I said, for everything else that we could. And so if you look at the large match groups, which are more trustworthy because they have upwards of hundreds of units in them, you can see that almost all of those match groups have a negative estimated treatment effect. Whereas, for the smaller, untrustworthy match groups, you see more variance, and that's what you'd expect. So this is a pretty strong result. We did not see the strength of this type of result when we looked at other types of outcomes, like, for example, being in the intensive care unit. We didn't see this kind of very strong signal on the treatment effect. All right, and I want to show you one of the match groups. And what you can see from this match group is that everybody has identical covariates. So it's a very, very nice match group. These are all teenagers. So the mothers and the fathers are both teenagers. The mother doesn't have a diploma. They were all born on a Tuesday. The father's race was all white. The mother's race was white. The infants were all male. The mothers didn't have any health conditions. It was like a very, very tight match group. All right, so the takeaway is that matching is interpretable, but only if you match almost exactly. And, all other matching methods are either uninterpretable, like propensity score or prognostic scores, or they force the user to choose how to match, and this forces the user to do high dimensional optimization in their head. Our methods are the only methods for adaptive, interpretable, large-scale matching. And they all have they follow this framework where they use machine learning on a training set to figure out how to do the matching. They are very scalable. They work on very big data sets. They are fast. You can get results in minutes. Even in large data sets, you can get results in like an hour and a half or so. They're very accurate. And they provide granular insights that other methods cannot provide. I hope your main takeaway from this talk is that matching methods are extremely powerful, not just because they're non-parametric, but also because they're interpretable. Thank you.
Questions?
Okay, so there is a question in the chat here, which is whether theta is determined or a decision variable. So it is a decision variable that is determined from machine learning on the training set. And that's the whole point of machine learning on the training set. It's to figure out what theta is for each match group.
Okay, and we have a question in the room.
The question is also with theta, the algorithm chosen, I think it was least squared mean to do your isolation.
Just least, it was just least, I mean, it's like regular as least squares. You can pick whatever algorithm you want.
That was the question.
It's just a parameter.
How did you arrive there, and is it swappable to do the isolation?
It's swappable.
Okay.
Yeah. There is a question in the chat, which is there a way to get something like an AUC curve? You mean an ROC curve, I hope. So I'm not sure what you're talking about there, because this problem is like, it's not supervised. So, it's not clear, right? It's only half supervised. You can certainly get an ROC curve on the training set, and you can use AUC to help select your variables. But the only way to get causal estimates is to, in our approach, the way to get causal estimates is to match the group and then look at the outcomes for the treatment and control units. There's no ground truth on those treatment effects unless you do a simulation. So yeah, I don't know. I don't really know where that question's coming from. Okay.
I have a question regarding the number of matched size. For example, if the treatment is 10 and the traditional method is able to find 8 out of the 10, how is AME method compared to that?
So it's not about the number of units in the match group. Obviously more is better, but it's about the quality of the units in the group. So I'd rather have 8 really high quality matches than 10 crummy matches. If that makes sense.
Yeah, I was just trying to figure out, is there a sacrifice between the number versus the quality?
Well, I mean, certainly if you, okay, so I think you're thinking about you might be thinking about Malts rather than Flame and Dame. So for Malts, for Malts, you can look at the nearest neighbors, right? And those are in your match group. And if you have too many neighbors, you could lose the quality of the match group. But luckily, we have the distance metric, which is this stretch metric. And as long as the stretch metric is good, you can actually say things like, well, I don't want anybody who's more than distance of blah from me, because anybody who's that far out is not a good match for me, according to this learned distance metric. And so in that case, you could just say, I'd really like to include 10 nearest neighbors, but there's only really 5 that are any good. So I'm going to just pick those 5 because the others are too far away in this distance metric that I've learned.
Thanks.
Okay, and then there's a question over here. Have you been able to establish consistently better performance against other matching algorithms through your methods? Any pointers that can help justify this for a publication? So we've had many publications. Our group has written publications in JMLR and UAI, AI Stats. So we've done a number of of studies on both real data and simulated data. Simulated data being really useful because you have ground truth. And so you can, you have the treatment effects. So you can use the simulated data to figure out how good these algorithms really are against each other. And so we've been able to show that we've gotten consistently better results in terms of the quality of match groups than the other matching methods. And we've also been able to show that the accuracy of our approaches are equivalent to those of black box approaches that are known to be very accurate. In fact, they're as accurate as the state-of-the-art black box approaches. The best one is really Causal BART.
So in supply chain, the treatments or interventions don't tend to be binary. I mean, some are, but a lot of them are quantitative, like how much inventory should I hold, or even combinatorial, like what route should a truck take? Is there some possibility to extend this to more complicated kinds of questions like that, or do the matching groups just get too small in that case unless you have a huge amount of data?
That's a great question. We're actually working on an extension of Malts to that case because I think Malts can be extended directly to the case of real value treatments.
Great. Thank you.
Yeah, you basically have to match units that are close to each other in the other covariates, but different from each other in the treatment. So as long as there's a variety of treatment values within the match group, then you can estimate treatment effects.
Great, thank you. Well, I think with that, we'll thank our speaker.